Okay, well, here's a report. Now, this appeared in Nature, the prestigious British Journal of Science in 1974, the same year as the one we were just quoting from. This is deep drilling in an active geothermal area in the Azores. So in 1972, geoscientists from Dalhousie University and Lamont Doherty Geological Observatory initiated a deep drilling program into the oceanic crust. Our second borehole in 1973 was located on the island of São Miguel in the Azores. And an initial report is presented here of the 981 meters penetration of a complex sequence of subaerial and submarine lavas, pyroclastics, and volcanogenic sediments. We've defined the term subaerial, means in the atmosphere. Submarine, below the water. Pyroclastics are solid pieces of material that are part of a volcanic eruption. Like you've heard of a pyroclastic flow when you have a major, like an explosive eruption, and you have this big, almost like tidal wave of material sweeping down the sides of the mountains that are, so deadly. Yeah. That's the pyroclastic flow. Volcanogenic simply means or having its genesis in a volcanic eruption, right? So what they did, they had 981 meters of core they brought up, and what they found was a complex sequence of atmospheric and submarine lavas, pyroclastic material, and volcanogenic sediments. I'll skip a couple here because it's not that directly relevant, but get right here to the crux of it. A surprising result of our experiment has been the depth at which submarine deposits were encountered. Subaerial or shallow marine conditions, now this is both atmospheric and shallow marine, meaning less than probably 100 or 200 feet, maybe 10, 20, 30 feet, just along a shoreline, right? So they found subaerial or shallow marine conditions are found 786 meters below present sea level and indicate substantial subsidence of the island. So, duh. So we're talking 2,580 feet. That's half a mile. That's half a freaking mile. Okay. Yeah. Man, it goes on. We're just barely getting into this, but it's interesting that we can go back to Atlantis from the geologic point of view. In light of what is known today about the ocean floors, now this is written in 1978, okay? Now, just given what we already have learned in these podcasts, think about this, what they're saying here. In light of what is known today about the ocean floors, we can definitely rule out the possibility of a sunken landmass of any substantial size in the Atlantic. Or, for that matter, in any other ocean basin.
Lies.
And then, nowhere in the ocean basins is there any sign of a large mass of continental-type crust, which could represent a submerged continent. Wait. Time out. I agree with that, right? Yeah. And from what you guys now know, you would be agreeing with that too. Yeah, there's, but let's define what we mean by large. Well, they're saying a submerged continent. Well, the smallest continent on Earth is Australia. So it's got to be at least as big as Australia or bigger to fit the definition of a continent. But nowhere was anybody ever talking about that except in the woo-woo. Plato never talked about a continent, right?
That's right.
He talked about islands.
Yep.
So then, with an Atlantic site ruled out as physically impossible, all arguments based on racial, linguistic, or other cultural similarities on both sides of the ocean, which would include the rest of Ignatius Donnelly's 13 propositions, must collapse. Either they are not real similarities at all, or they must be explained in other ways, including mere coincidence. Yeah. And so that was considered to be the final word on the matter in 1978. And what you see is post late 1970s, everybody starts going everywhere else and saying, oh, here I found Atlantis. It's over here.
Yeah.
Well, I found Atlantis over here. And here's why this guy is wrong, but here's why I'm right. And here's how we have to figure that Plato, Plato was mistaken about this detail or that detail. And what he really meant was this that supports where I think Atlantis was. Now, that's not to say that some of the things that you're talking about aren't interesting, because a lot of them really are. But then to try to say, well, this is Atlantis, the question in my mind has always been, how far can we deviate from Plato's account and still legitimately call it Atlantis?
Yeah. None.
Well, at this point, we're going to have to come back to Plato, because obviously we've not covered a lot of his details. But with this background and this context, once we go back and we start looking at some of his details, I think we'll have a more insight into the whole story of Atlantis. And so, yeah, I think, did we quote from The Sunken Kingdom, The Atlantis Mystery Solved?
I don't know.
The possibility of a real Atlantis in the terms that Plato described it has long gone. That's his working premise. This came out this was a book in 1996. He says nearly 2,400 years ago, the Greek philosopher Plato posed a riddle which has baffled scholars ever since. Was the story of the lost continent of Atlantis a complete fabrication, or did some historical reality lie behind it? The possibility of a real Atlantis in the terms that Plato described it has long gone. To which I would go, oh, really?
Yeah. He also said continent there.
Yeah, and then for all its romantic appeal, the idea of a prehistoric super civilization on an Atlantic continent is vanishingly unlikely. But again, in science, you got to define your terms. So I would ask, what the hell do you mean by a super civilization?
Yeah.
Let's define that. And then I think we can reject the use of the term continent, because that was not Plato's term. I mean, Plato's terms he used were well-known Greek terms for island or islands. Okay, let's go on. We'll talk about these seamounts. We introduced seamounts last episode, right? Right over here, cursor is over the Pillars of Hercules, which is the Straits of Gibraltar. Inside, we have the Mediterranean. Outside, we have the Atlantic Ocean. And if we follow this dotted line here, this is the fracture zone, right? So you got the African plate down here. We've got the Eurasian plate here and the North American plate over here. And this dashed line represents the crack, if you will, between the Eurasian plate and the African plate. And it comes over here, and then it transects, it cuts into this elevated region on the ocean floor, and it cuts right across this, and then it meets the suture zone or the fracture line between these two plates and the North American plate. And so what we have here is a triple plate junction, which obviously would be, and just, yeah, logically would be a zone where you would think there would be the most flexibility in terms of isostatic adjustments, right?
Yep.
And then we've got, you can see there, these little dots. I'll pull up some better maps of them, but these are the Azores, which are actually just mountaintops whose bases are sitting in this, if you want to call it, a microcontinent right here.
Yeah.
And then south of there, you've got these cluster of seamounts right here. And I believe, yes, there we go. So they're named, here's the Azores Islands. And then we've got, curiously named, the Atlantis Seamount here, Plato Seamount right here, Great Meteor Seamount, another interesting connection and coincidence. Make Great Meteor Seamount here, and then the Cruiser Seamount right here. So we've got these seamounts. Now let's see what we learn about seamounts. I'm going to skip a couple of things here, and here's a section looking at the Great Meteor Seamount, an east-west cross section, and you can see here the vertical scale is exaggerated to make it more prominent. It isn't quite this dramatic coming up off of the ocean floor, but that's what it looks like in profile. And here would be a bathymetric map of it, right? And the important thing to note here is the flat summit of it. We'll go through here, and here's the Atlantis seamount. Okay, so here we have a flat top again, and we have, so here's the profile of the submerged sea map, and here's the contour intervals, the map showing the contours and the depths of these things. This is a contour interval. Okay, so this is in fathoms. So 500 fathoms would be 3,000 feet, roughly, if a fathom is 6 feet. Yeah, and here, over here in this one, you can see the depth of the top of the thing. Here's at about 400, roughly 400 fathoms. And here's the Atlantis seamount, which got changed to the Atlantic seamount, because you wouldn't want to have anybody thinking that, that they meant to imply that this was Atlantis. Can't have that.
How big are those seamounts? You would.
Well, okay.
The tops of those plateaus. What's the width? What's the width?
Okay, right here. This is 34 degrees north right here, and this is 34 degrees 10 minutes. We could figure out from that. Wouldn't be hard to do. Let's see. Let's take a look right here. Well, okay, so
I mean, there are no distance measurements here that I can tell.
Will that distance change as you go further and further north, right? Like 10 minutes of degrees, it'll change, won't it?
Yeah, but for rough purposes, it's 20, let's see. Okay, so we're looking about one mile per minute here at this latitude. 10 miles here.
It's a decent sized mountain.
Yeah.
Yeah.
Or plateau, if it's shaved off, it plateau.
Plateau, yeah. And here they show pretty clearly on this map.
So the question is, with all these flat-topped mountains, what made them flat-topped?
What made them flat? See, that's the question, right?
I mean, and they're all flat-topped at pretty much the same height.
Right. Okay, well, here's how you explain it. And we can actually pull up some scientific research on this. You've got mountain peak above the ocean, and now you have a highly turbulent, erosive ocean that is basically, you have to have a means of shearing off the tops of these mountains.
Yeah.
And because they're basically at the same level, that shows you that this shearing force was applied in a plane. It wasn't differential. It was in a plane. What I've got up here now is a bathymetric sketch of Atlantis Cruiser and Great Meteor seamounts. Great Meteor, Cruiser, Atlantis is over here. Reproduced from The Face of the Deep by Heezen and Hollister, 1971. Bruce Heezen, by the way, was one of the founding fathers of marine geology. And tragically, he died in a submersible accident down doing research. The caption for this image reads, "Ancient Sunken Islands of the Eastern Atlantic." And here they are, showing how the tops have been sheared off. And here's what they would have looked like before shearing.
Oh, yeah.
They would have been prominent, sharp mountain peaks rising up out of the ocean. So yeah, you can look up Neptune's Trident and you'll find some interesting bits. So here we go. You can see very clearly the sutures. You can see the stretch marks emanating laterally from the sutures. So I'm going to stop share for the moment, give people a chance to digest. All right, so let's get back to some of the science here. This is from Honorez, if I'm pronouncing that right, Jay Honorez, and a group of others who published in Earth and Planetary Science Letters an article entitled Mesozoic Limestone from the Bima Offset Zone, Mid-Atlantic Ridge. Now this is south of the Azores, but the same principle applies to this idea of vertical movement along the Mid-Atlantic Ridge, right? So in an earlier paper, Bonatti and Honorez report dredging a shallow water limestone from the summit of a transverse ridge within the offset zone of the Mid-Atlantic Ridge. The limestone was reported to contain detrital grains of quartz, orthoclase, and microcline, indicating You don't need to know what that is for right now. Although what you need to know is that it indicates that there was a nearby source of granitic detritus, which was available during its deposition. Bonatti and Honorez have unsuccessfully attempted to explain their findings of granitic material and shallow water limestones on the basis of the present or recent geographical configuration of the equatorial Atlantic. They suggested that the limestone and its granitic mineral grains must have been deposited sometime during the Mesozoic, which of course brings us back into the age of the dinosaurs, right? We have to go back at least 66 million years.
Yeah.
Soon after the opening of the Atlantic Rift. Well and good. Within a narrow and shallow proto-Atlantic basin. If Bonatti and Honorez's interpretation is correct, it would require that the crustal block capped by the limestone was left behind during the spreading of the Atlantic floor. This possibility would have important implications. I'm going to skip over some of the really technical stuff, but they're looking at the evidence of the oxygen isotope ratios and the carbon ratios, carbon 12 and carbon 13, oxygen 16 and oxygen 18, and found that they had strongly negative values. What does that mean? Well, it means that in both cases, it's a clear indication of subaerial recrystallization. Only through the action of meteoritic water, which means rainfall, enriched in light carbon while passing through a soil zone, can the observed isotopic values be explained. So in other words, you're talking about something that's above the surface of the ocean. There's soil there, right?
Right.
Soil.
Yeah.
Right. Okay.
Dirt.
Dirt. Yes, dirt. The conclusions we derived from this study appear to confirm and extend the results obtained previously by Bonatti and Honorez as follows. The components of the limestone constitute a homogeneous assemblage characteristic of a shallow water carbonate platform depositional environment. The crustal block capped by the limestone must have undergone large vertical movements, including episodes of immersion. Immersion, coming out, like immersion would be going into the water, immersion coming out of the water, right? Large vertical movements where these blocks are coming up out of the ocean. If crustal spreading took place in this area at rates of about 1.2 centimeters per year, the block capped by the limestone apparently did not move with the spreading floor. We're going to jump.
Floated.
So then we have an editorial comment on this work that I was just quoting from. This appeared in The New Scientist, 1975, volume 66, number 952, page 540. Although they make no such fanciful claim from their results to have discovered the mythical mid-Atlantic landmass, of course, they would not even consider making such a fanciful claim.
Right.
Although they make no such fanciful claim from the results as to have discovered the mythical mid-Atlantic landmass, an international group of oceanographers has now convincingly confirmed preliminary findings that a sunken block of continent lies in the middle of the friggin' Atlantic Ocean. And I think that is the first documented use of the term friggin' in the scientific literature.
Yeah. Although they make no claims that this was Atlantis, they basically found Atlantis.
4 years ago, two University of Miami workers, J. Honorez and E. Bonatti, first reported the recovery of shallow water limestone fragments from the Vima fracture zone. This limestone contained minerals indicative of a nearby granitic source unlikely to occur on the ocean floor. The limestones include traces of shallow water fossils, foraminifera, green algae, bits of gastropods, and crab coprolites, implying formation in water, in one instance, less than 30 meters deep, about 100 feet. Furthermore, the limestones have been recrystallized from a high to low magnesium form of calcite, which is the thing that I was referring to earlier, that I left out the technical details. Oxygen and carbon isotope ratios prove conclusively that this process must have taken place subaerially. So, I mean, there we go. Then 2 years later, Ibanati and others, and another group of oceanographers and marine geologists published yet another paper entitled Neogene Crustal Immersion and Subsidence at the Romanche Fracture Zone, Equatorial Atlantic. According to plate tectonic theory, the motions of lithospheric plates between an accretionary boundary or a spreading center and a consumptive boundary or a subduction zone, right, are essentially horizontal, taking place on the outer shell of the globe. However, some exceptions to this model appeared to obtain in the vicinity of major oceanic fracture zones. Yeah, that was my thought exactly. In this paper, we present an example of vertical tectonism of a transverse crustal block located on the north side of the Romanche fracture zone. We demonstrate that the summit of this block was at or above sea level during the late Cenozoic, which geologically speaking was yesterday. So what their conclusion is that it has been suggested that the transverse morphology, Bonatti called attention to the significance of prominent east-west transverse ridges, which I will do a quick screen share here because they show up really nice on this particular map right here. And get back to these transverse ridges. And that's these east-west, which I like in last episode to basically Earth stretch marks. So that's what he's talking about here. Bonatti called attention to the significance of prominent east-west transverse ridges, some shown already by Heezen and others, which run parallel to the equatorial Atlantic fracture zones. It has been suggested that such transverse morphology associated with fracture zones could not have been produced solely by crustal spreading from axial segments of the mid-Atlantic ridge, but that vertical tectonic motions exceeding those predicted by a simple plate tectonic model must have operated. So right there, those what I'm calling the stretch marks are like the evidence. What he's calling here that they're evidence that vertical tectonic motions exceeding those predicted by a simple plate tectonic model must have operated.
Right. So those transverse ridges were made by massive vertical movements at that.
It makes sense too, because it's like when you're looking at the map, it looks flat, but really it's curved like this. So if it was going to be pushed out, it would have to crack all along that main fissure because it's actually round.
Yeah.
You know what I'm saying? Unless this is Flat Earth Society over here. It would, on a flat surface, it could rise up like this without having these cracks running this way. But because it's curved, it's got a crack in both axes.
Yeah, in order to expand outwards. And that's right.
Yeah. By Enrico Bonatti, published in 1978, also in Earth and Planetary Science Letters, is entitled Vertical Tectonism in Oceanic Fracture Zones. He says, in this paper, I will focus attention on another class of exceptions to the age depth of the oceanic crust relationship, namely on anomalies associated with large oceanic fracture zones. I will present examples from the Atlantic and Indian Oceans which suggest strong vertical tectonism to be characteristic of the large fracture zones. A qualitative estimate of vertical motions of the crust at the Romanche fracture zone was made possible in one case by the recovery of datable shallow water limestones from the summit of the transverse ridge, which is presently about 3,200 feet below sea level. On the north side of the Romanche Valley, these limestones were formed close to sea level about 5 million years ago but subsequently have undergone episodes of immersion. In other words, they've come up and been exposed to the atmosphere.
Right. Wow.
The data discussed in this paper indicate that, get this, intense vertical tectonism of upper mantle and crustal blocks occurs along the large oceanic fracture zones. This vertical tectonism causes motions which exceed by far the small relative vertical motions of the type discussed recently. In other words, what they've discovered here in the 70s is that there has been this massive movement of the ocean floor concentrated along the oceanic fracture zones.